Well, good morning. Today's topic is spectroscopy. Now, people typically visualize that word as visual spectrum measurements, like a rainbow. That is, it could be spectroscopy could be used to analyze a rainbow, and it is an effect of one of the analytic methods that creates the rainbow. So we can reproduce that in a lab instrument. Now, spectroscopy is a word you need to go look up. And there's a Wiktionary definition that's really good about it because it doesn't point to optical emissions, it points to emissions analysis. So spectroscopy is the analysis of emission waveforms into analytic information. So the waveforms are analytic or analog functions that we turn into digital signals to analyze them. But we're still analyzing analog signals. We're looking for analog questions, and if we answer them, they're now a binary answer. We can say yes or no, that's there. So this spectrum analysis idea rolled back into an instrument. So what types of instruments do spectrum analysis? Nearly most you can think of. Now, an oscilloscope only displays a waveform. The user of the oscilloscope used to have to interpret everything about that waveform, and they really are simple machines in their complexity, but they've gotten so much better that you take for granted what they do for you now. It used to be on paper and slide rules, and so spectroscopy is a very, very old science. It ends up, spectroscopy is even a titration, a litmus strip, because it's a separation of elements inside whatever you're testing, a liquid in this case for titration strips typically, although there are titration strips for atmospheres too. So spectrum analysis is a huge field, and it gets very specific depending upon what the spectrum you're looking at is. So optical emissions, that's the rainbow. That's the spectrum of light that the sun gives off that we can see through our atmosphere. So the bulk of it's actually filtered out by our atmosphere. Even on a clear day, a lot of elements are filtered out. We don't see, they never get to our eyes to see them. So, but they're there. So we put an instrument in space, so it's beyond whatever refraction indexes our own air causes, and you get much better resolution on distant things and much more precision because you don't have to worry about things like earthquake shakes or a truck driving by your instruments. So spectrum analysis is a huge, massive field, and when you get into it, remember you're trying to turn an analog signal into a decision, a binary decision. So you have to understand how to dissect the waveform. Now you're getting into signal analysis, you're getting into pattern analysis, you're getting into signal discretion, signal to noise ratios, you're getting into analytics of things that are all theoretical and math, but they work, they're proven, they work consistently and over again against what we see in nature when we drop a ball and E equals mc squared. So this spectrometry thing is just a huge part of the measurement sciences and physics. Now, why would you wonder or delve into what this is. Let's take a gas spectrometer as an instrument example. Gas spectrometer takes a gas sample from somewhere, and it takes a micro sample of that in picoliters. It injects it into a fractioning column, and the fractioning column will separate basically the heavies from the lights, or the largest from the smalls. So the first thing off the top of that column are light elements. Hydrogen is a good one. Oxygen's actually a slow one because it's a large element and it binds as O2, so now it's a molecule. So a lot of elements do that, like nitrogen binds as N2 in its free form. So it's a little bit slower coming out of a column. So what can you use that for? Well, if you do this thing right, and it's timing, logistics, and sample rates, and temperatures, and PV equals nRTs, the first thing you'll get off the top of that column, depending on the materials in the column, is a hydrogen. So now you can harvest hydrogen by just taking the top piece of that column and then discarding the rest, and then you inject another sample in there and you take the hydrogen off the top of that sample. You might only be taking picoliters off of a picoliter sample. So you're not talking big volumes unless you upscale the process, which Union Carbide did one of those really cool pressure swing absorber, harvested hydrogen from a syngas generator to use further down in the process, 99.99% pure hydrogen. So there's an industrial applications, gas chromatograph. So how does a gas chromatograph work? You've got a standard gas, you've got a carrier gas, and then you've got sample gas. And you use those things to make sure your instrument's working correctly. You watch the timing on it. You watch a little instrument called a Wheatstone bridge. And that Wheatstone bridge is used in a differential measurement of carrier gas to sample gas. So half the Wheatstone bridge is exposed to carrier, the other half is exposed to sample, and the minute differences in the temperature taken off of the Wheatstone bridge elements causes a resistance change which can be measured. So now I have an idea of the density of the materials flowing across the Wheatstone bridge on the output side of a capillary column inside a gas spectrometer, doing real-time samples 24 hours a day for months and years at a time without failing. That's what you strive for. And was one of my jobs in a plant, is making those types of instruments run for years without having any question in their accuracy. Or that was a goal. Some of them only ran months before you had to do something with them, but they got better as I worked on them. So spectroscopy is a huge field. Second spectroscopy thing I was rather familiar with is optical emission spectroscopy, where you take a very, very bright light source, you put it into a optical system that can separate the light. So all the colors of the light spectrum hit different detectors of an array, and the electronics measures the intensity of those and tells you what elements are coming out. So that's optical emission spectrometry, and it's typically associated with what your eyes can see, but optical emissions are well below and above that with what instruments can see. So we can't visualize it. It's like we can feel heat, but we don't really see heat necessarily. Yes, it might be red hot, so you see heat, but it also could just be black hot, and it's still hot enough to burn your little pinky when you put it on there. So children bewares, right? Watch the stove. Anyone who's been around a cast iron stove and children has got to have some idea of what could happen compared to today's nice, reasonably safe gas stoves. But you can't see that heat. especially a child, can't see that black heat. The stove can be 200 degrees, it's not red, but that is enough to fry bacon, so it'll fry a little hand. So that's spectroscopy. But you went from visual spectroscopy to the senses, to the heat, which is a thermal spectroscopy. And then when you actually singe your nerves, that's an ouchie. That's not spectroscopy. See a doctor. So what else is spectroscopy out there? Satellite imagery, hidden inside even a film photograph taken from a satellite of the Earth or taken outwards towards the stars. The film has a very specific and engineered spectrum response. We know exactly, calibrated, measured, and certified that the film that went up there can see exactly these wavelengths. So they're visualized as colors on film that we can see, but they can also be filtered and put on film as infrared images that show heat. And we've only gotten better at this stuff, not worse. So there's spectrum analysis, is that helicopter that flies over looking for heat signatures from forests and plants and trees. Another helicopter with spectrum analysis is run by the Department of Energy to do high spectrum energy measurements over a localized area. And you can find out about that in helicopter patterns flown over the city of Seattle as one example. And in those patterns, they didn't disclose the location, but it did find a cancer treatment patient that was in their house and undergoing cancer treatment, and their personal body radioactivity was enough to set off alarms and triggers to that Department of Energy survey team. So there's another set of maps. And I can refer you all over the place to these maps. If I began putting links in these videos, you'd have a list of links that comes nowhere close to mine anyway. So by finding these things yourself, you're just better off for it. So the word for the day was spectroscopy. Gave you a little few hints where it's used. It is an analytic methodology tied specifically to an instrument's capabilities, and all that's tied to the idiot with the on-off button. So there's a few of those around, on-off buttons. You never know who's pressing them. Have a good day, and we'll see how this one looks again. It'll probably go up. I got a stockpile of a few